Hi everyone! In this video, we will learn how to draw a dinucleotide. As a quick reminder, a nucleotide is a building block of nucleic acids. It's a monomer of nucleic acids. Some people call a nucleotide a base, but a base indeed is only a part of the nucleotide along with the ribose and the phosphate. We will be making 3 drawings in total. So you will need a blank page. In the top third, we'll draw the 2 nucleotides as you can see them right here in front of you. Now, in the next third of the page, you're going to be showing the formation of a new ester bond. I'm going to be using a green color to point at the formation of the new ester bond. Do you see my big arrow pointing at the formation of the new ester bond? Okay. You will also be showing how the pyrophosphate, the diphosphate comes off, and a water molecule coming off. And in the third drawing, you will show the final product. Okay? So the final product is actually the formation of 2 nucleotides together. Okay? I will show you and point that already a phosphoester bond existed, but the important one is the formation of the new phosphoester bond between one and the other nucleotide. This one is the old phosphoester bond, and this one is the new phosphoester bond. So the main objective today is to show you how the new phosphoester bond is formed and how this dinucleotide is formed. So let's get started from scratch. You're going to need a whiteboard, and we're going to get started by drawing a ribose sugar. Okay? A ribose sugar is similar to a cartoon house. It has an oxygen on top of the roof, and it has 4 carbons, carbon 1, carbon 2, carbon 3, carbon 4, and the chimney, carbon 5. Now, you will be wondering, why do I put the prime next to each carbon? It's because attached to carbon 1, we have a nitrogenous base. And I'm going to depict it this way, a nitrogenous base. Within the base, there are carbons, and we mark those also as carbon 1, 2, 3, and so on. So therefore, for the ribose sugar, we're going to be using carbon 1, 2, 3, 4, 5 prime. Now, make sure you know that each carbon has 4 bonds, so carbon 1 must have a 4th bond with a hydrogen, and carbon 2 will also have 4 bonds. It has 1 with carbon 1, 1 with carbon 3, and 2 more hydrogens. I'm drawing a deoxynucleotide. If this was an RNA, I would be adding an oxygen here, a hydroxyl group attached to carbon 2. But because I'm drawing DNA, I am not going to add a hydroxyl group. So let's move to carbon 3. It has 2 bonds. So this one does have a hydroxyl group plus a hydrogen. Carbon 4 has 1 more hydrogen, 1, 2, 3, 4 bonds. Carbon 5 will have 2 more hydrogens here, and then an ester bond. Remember before I told you there is an ester bond that already existed. Here is the ester, the old ester bond. Okay, and there will be 3 phosphates here. Oops. This is an oxygen. Okay, and 3 phosphates. Okay, 1, 2, 3, with an OH here, a double oxygen here. Okay, and for simplicity reasons, I'm going to put a hydroxyl group down here. I could put negative oxygen. At pH 7, you have between 1.4 and 2 negative charges, but I just put hydroxyl groups instead. Okay, and let's plan it correctly. So right underneath this hydroxyl group right here, I'm going to start drawing a phosphate. Okay, and this phosphate also is esterified to the carbon 5 prime. Do you remember the chimney of the ribose sugar? Okay, so we're drawing now a second nucleotide. One of them is complete. Let's draw the second one. So this one has carbon 1 prime, carbon 2 prime, carbon 3 prime, carbon 4 prime, and carbon 5 I already drew. So let's make sure we do it all correctly. So at this point, carbon 1 has a nitrogenous base attached to it, and it has 1 more hydrogen. Carbon 2 has 2 hydrogens. Carbon 3 has a hydroxyl group and a hydrogen. Carbon 4 needs a 4 bond here. Carbon 5, 2 more bonds right here. Lots of covalent bonds. And here I am not going to make the mistake that I did a second ago. I'm going to add 3 more phosphate groups. So right here, I'm going to flip this one because they can flip in space. So I'm going to mark it in red, this alpha phosphorus atom, okay? And I'm going to circle it for you so you can see. And this phosphorus atom has covalent bonds around it. The whole thing, it's called a phosphate group, okay? And here you have 2 more of those. So let's complete correctly all these other phosphate groups with double bonds here and hydroxyl bonds underneath it. So at this point, what I would like to do, I'm going to circle each nucleotide with a green marker so that you can see they're still separated. Still separated. So this is 1 nucleotide, and this one below, it's a second mononucleotide. Okay? So what I want to show you next is the ester bond formation. I would like for you to pay attention to my blue color, and you can see the oxygen has pairs of electrons right here. A pair of electrons from this oxygen within this hydroxyl group attached to the C3', to the carbon 3' carbon. This pair of electrons, I'm going to show you, there will be a nucleophilic attack. A nucleophilic attack where the pair of electrons attack the alpha phosphorus atom. At the same time, a pair of electrons from this double bond, okay, they move right here. So what happens? Because this oxygen up here this oxygen up here, part of the hydroxyl group, has lost a pair of electrons, I'm going to put a purple sign. It became positively charged. Now, the second oxygen right here, I put a purple arrow. This one has gained a pair of electrons, so it becomes negatively charged. Okay? So, at this point, I'm going to use the eraser to redraw for you what exactly has happened. Okay, so I'm going to redraw the upper carbon 1, 2, 3, 4, 5. And this one has all the phosphates attached. Here is the last one. And with the double bonds of oxygen up here, hydroxyl groups below. Double bond here, hydroxyl group below. Okay, this one has 2 hydrogens. Okay. One and 2. This one has 1. This one has the hydroxyl group and 1 more. This one has 2. This one has 1 hydrogen and 1 nitrogenous base. Okay. So I just showed you a minute ago. This is the alpha phosphorus atom with an OH here, a double bond down here. And this one is esterified to the C5, which is connected to the ribose of the nucleotide below, C1 prime, C2 prime, C3, C4 prime. This one has 2 hydrogens. This one has 1 and the nitrogenous base. This one has 2 hydrogens, hydroxyl group and the hydrogen, and this one has 1 hydrogen. So why did I redraw this for you? I redrew it because just a minute ago I was showing you the movement of electrons. Okay, so the movement of electrons from here to here, from here to here, making this oxygen of the hydroxyl group become positively charged, making this oxygen become negatively charged. Okay, and I want to emphasize right here that the pyrophosphate has left. Okay, so the pyrophosphate has left. We call it diphosphate or pyrophosphate. I'm going to circle it in red. Okay, we call it PPI or diphosphate. So this one has left, okay? And please notice also in order to make an ester, a water molecule will depart. Okay, a water molecule right here will depart, and an ester bond, I'm going to make it in red, will unite the oxygen of the hydroxyl group above and the alpha phosphorus atom below, of the nucleotide below. Okay, so before water can depart, okay, we have deprotonation of this oxygen, so this hydrogen ion moves out, okay? And it will unite with the hydroxyl group below to make the water molecule, okay? Now the double bond right here, which was lost initially when the pair of electrons had moved back onto this oxygen, is being reformed, and at the same time the water molecule, so the double bond is remade and the water molecule will leave. So we lost a pyrophosphate, we lost a water molecule, okay? But what we have gained a dinucleotide. So in conclusion, okay, I want to show you the final product. The final product is a dinucleotide, two nucleotides bound together, okay? And they're bound, I'm going to use the green color, by this phosphoester bond. This is the new phosphoester bond, okay? Now, there is already a phosphoester bond right here, okay? And because of that, the two together, we call it a phosphodiester bond. The new nucleotides are always added from 5' towards 3' direction. And I want to explain that to you in a minute by showing you some diagrams from your book, okay? I would like, first of all, for you to pay attention to the diagram in your book, which shows you how through hydrolysis, the loss of a water molecule, the 3 phosphates, here they're circled in orange, they're being added to the C5' carbon, okay? And that's how you end up with a mononucleotide with a ribose sugar, which we drew before, the 3 phosphates, and the nitrogenous base. I can immediately tell that we're talking about DNA here. Why DNA? Because I can see that there is an oxygen missing on the second carbon. The basis of DNA could be adenine, thymine, guanine, or cytosine. If this were RNA, then right here on the second carbon, we would have an OH instead of an H, and the basis would be adenine, uracil, guanine, or cytosine, okay? So I would like now to show you the next image from your book, and you can see this one is an RNA nucleotide, okay? How do I know it's RNA? Because it has the hydroxyl group on the second carbon, and because it has a uracil as a nitrogenous base. So this one is a mononucleotide triphosphate. It has all 3 phosphates, okay? And the last image from your book that I would like for you to refer to, it's actually the growing chain of nucleotides, okay? The addition of a new nucleotide to the growing chain. So I'm going to circle the new incoming nucleotide right here, okay? And the 5' triphosphate contributes all the energy to form the ester bond, okay? And it explains why only nucleotide triphosphates, 1, 2, 3, triphosphates are added to the growing nucleic acid chains. One cannot break a phosphodiester bond and then reform it, because the triphosphate energy can only be spent once. So cells do their best to get it right when they add the new nucleotides to the nucleic acid chain, because it is expensive to make a mistake. So once the new nucleotide is added, okay, a phosphoester bond forms between the alpha phosphate and the okay, so this oxygen, here we have C3, okay, this was the alpha phosphate, and here is C5, okay. So if you look better, you can see here on top of this chain, you can see that this is C5 prime, okay, and down here, the hydroxyl group down here is attached to the C3 prime. And because of that, the direction, okay, this is 5 prime, this is 3 prime, okay, it's always being added 5 prime towards 3 prime,